Hello and welcome to the Daily Space for today, Tuesday, April 14th, 2020. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Sometimes astronomy giveth, and sometimes it takes away. Today we have both times two. In our first story, the Instituto de Astrofísica y Ciências de Espaço has announced that scientists using the integral field spectroscopy instrument have studied the central bulges of spiral galaxies to understand the factors that cause the bulges to grow. Over several years, they computationally chewed through approximately 500,000 spectra that covered all possible variations of non-interacting spiral galaxies. They did large, they did small, they did, every combination of disk, bulge, and arm, as they hope to identify exactly what physical characteristics are linked together. With this data, the team was able to measure, among other things, how stellar ages vary across the galactic bulge as a function of kind of galaxy. Like many things now being determined with data, these results run a bit counter to what we would have expected a few years ago. Specifically, they found that in low-mass spiral galaxies, stars go from young to old as you move out from the center, while in high-mass galaxies, stars run from old in the core to young as you move out. Yes, folks, the distribution of stars by age flips around as you increase a galaxy's mass. This happens even though the galaxies themselves appear to form in the same manner through the aggregation of smaller systems into larger and larger galaxies. And this difference in stellar populations appears to be related to past active galactic nuclei behavior that is only seen in the largest of spiral galaxies. In these particular bulges, where once a black hole actively fed, radiation blasted out and cleared the core of the galaxy, while pushing material to outer areas where star formation continued. Overall, they find the process of growing galaxy bulges is a slow and gradual process, with bulges forming over 2 to 4 billion years, and an active galactic nuclei defining flipping point where the galactic core goes from densest in the core with star formation to empty in the core due to light pressure. Well, they're still working to figure out exactly where in the mass distribution that flip most often takes place. This work should allow detailed models to be created that allow us to step through the process of bulge formation by looking at systems of every intermediate age and size. This is just cool and straightforward research that is made so complex simply because of the computational power needed to, make this result possible. Again, folks, they looked through 500,000 spectra. These results are reported in the Astronomy and Astrophysics Journal, and this work was led by Iris Breda. This is a case of the universe giveth, the first case for today's news. Now, for the universe taking away, I have sad news to report. We can confirm that Comet Atlas has totally fallen to pieces, or at least to 3 pieces. In an astronomer's telegram, astronomer Zhangji Lin and collaborators report that in observations taken with the Lulin 40-centimeter telescope, they see a nucleus and 2 additional fragments trailing at 3,450 and 5,000 kilometers from the core of the comet. She's dead, Jim. No bright comet for us. There are some pretty amazing images, though. There is this one from Lulin and this one as well, where you can just start to make out that core that now appears in 3 places. Now, these are our new news stories for today. In just a moment, two special guests will be joining us to discuss results from 2 weeks ago. In a remarkable paper in the journal Nature, they described how Mercury may have held onto the kinds of volatile gases that are required for life, and it may have held onto these volatiles all the way up to maybe 1.8 billion years ago. In the deep hollows of the chaotic terrain, the broken landscape opposite the Chloris impact basin on Mercury may have once been capable of supporting life, ever so briefly. If this is the case, relics of prebiotic chemistry may be waiting to be discovered by some future Mercurial rovers that, to be fair, no one is currently planning to build. Volatiles gave the potential for life, and the heat of the sun baked that potential away. We're going to pause for just a moment here to bring on our guests. Don't go anywhere. When we return, we'll be joined by Doctors Deborah Domingue Lorin and Jeffrey Kargel of the Planetary Science Institute. As a reminder, the Daily Space is a product of the Planetary Science Institute, so be particularly nice. Stay tuned. I will be right back as long as Zoom lets me. Stay tuned. Hello, everyone, and I am back with Dr. Jeff Kargel, and it's so exciting to have you here. And I'm sorry that we're still waiting on Deborah to join us. There was, as I said at the start of the show, a major update to Zoom, and a few things broke. So Jeff, you are here because you're part of some research that said some things I never thought I'd read in a peer-reviewed paper. Specifically, you said that once upon a time, 1.8 billion or more years ago, Mercury had the stuff of life. What made you even bother to go looking for it?
Well, first of all, I'm a co-author on the paper. The paper was led by our PSI colleague, Alexis Rodriguez, who's not going to be here today in this program. He has been interested for a long time in Martian chaotic terrain, jumbled up terrain that was produced by both the sublimation and the melting of ground ice. And the terrain just collapsed and became jumbled up. In some cases, giant floods ensued. And he noticed that there was a similarity between Mercury's chaotic terrain and Martian chaotic terrain. Now, Mercury's chaotic terrain for a long time had been only interpreted as due to seismic disturbance by a gigantic impact. And it was thought that the seismic waves rolled around the planet and converged on the opposite side of the planet and caused huge earthquakes during that impact that created the Chloris impact basin. That interpretation had remained completely unchallenged until Alexis noted that the chaotic terrain is much, much younger than the Chloris impact. And so it looks like it could not have been, according to the crater counts, it could not have been the seismic disturbance due to Chloris. So he started thinking more in line of Martian chaotic terrain. He was thinking it would be maybe due to ice, and I think that's a possibility. Personally, I'm fairly skeptical that it would have been ice, but it could still have been water. It could have been due to the formation of a thick layer, a couple kilometers thick, a mile, even 2 miles thick of a water-bearing mineral assemblage like clay minerals. They contain water. It's water bound up in the crystal lattice of the minerals. And when these minerals are dehydrated due to heat, they collapse down to a smaller volume. And so I think that might be it. And there's a host of other materials that it could could have been that don't involve water.
And
Yeah.
I'm going to just let you know, in case you didn't see, that our collaborator Deborah is about ready to join us. While I add her into the screen, I'm going to bring up a image of Mercury that folks will be able to see, and they'll be able to hear your voices, but they won't be able to see you while I sort getting both of you on screen. So please hold on for just a moment. But while I get you both up on screen, so chaotic terrain, you describe it as being jumbled up. And Deborah, can you turn on your video, please?
Sure. Sorry about that.
Hi, Deborah.
Hi.
Are you social distancing? Oh, you're at home like I am. Yeah.
I'm at home. Hang on. I can just get rid of the virtual background.
Or maybe you're in China. Oh, okay. The
Actually, the virtual background.
like...
You know what, Jeff? I will join you in Arizona. How's that?
Oh, that's good. Yeah.
Apologies to everyone out there who can't currently see what they are talking about. I will have them back on screen in just a moment. I am just fighting the good fight, as one always does with Zoom. All right, so this should work.
So Deborah and I both have saguaro cacti in our backgrounds because we are in Arizona.
Well, I'm virtually in Arizona.
I'd
like to be in Arizona.
You're virtually okay. So that's just a virtual image.
That's a picture I took out of my hotel room last time that I was in town.
Okay, I see.
Tucson, but I live in Maryland, where it's sort of overcast right now and kind of on the cold side. So I'm in my sunny, happy place here.
It's always good to have sunny, happy places.
And I'm showing blue sky. There is not a single jet contrail. Not a single jet contrail anywhere in the sky. And it's been like this for several weeks. That's, the lack of air pollution is one side benefit to a very, very, very bad situation. But yeah. Hey, you got to count your blessings where you get them.
Yeah. Are either of you observational in the research that you do?
Fortunately, no. So that doesn't impact me. I don't say fortunately, it's unfortunate. I used to when I first started my career, and that was one of the fun parts of it, is going out to the telescopes. But now I'm basically use spacecraft image data for what I do.
And I'm the same. I also have a history of telescopic observations. When I was in 5th and 6th grade, I had a telescope, and I sure wore my moon map out, my National Geographic moon map. But yeah, so I'm mainly a spacecraft data person also, and a terrestrial field person.
I have to admit that while I was one of the most prolific observers in my cadre in graduate school, I also had more clouds by percentage than anyone in my cadre in graduate school or anyone else. It got to the point that when the near Earth asteroid people showed up and saw I was on the mountains and saw clouds, they just drove back to Austin 8 hours away because they knew it was going to be hopeless. So I use spacecraft and survey data that already exists, because I also had a spacecraft I was planning to use blow up. So yeah, some people are meant to be the tail end of the unlucky distribution. But this is neither here nor there, because we're talking about a research paper where the data already exists and is already published. So the story we've had painted so far is lead author on this work, Alexis Rodriguez, who was unable to join us today. He was looking at the similarities in terrain features between Mars, where we have chaotic landscapes that have been torn apart through the escape of volatiles, and looking at similar looking landscapes on Mercury. And well, if science one world works one way, it should work the same way once you take into account temperature and compositional and gravity differences. It should work the same on other worlds. And he approached you and the other co-authors and essentially said, look, this looks like this world once was rich in volatiles or water or one of these other substances that would escape the soils and tear the world apart. What were your first thoughts, and what did it take for him to prove to you that this was the case?
So this wasn't the first evidence that Mercury contained volatiles. One of the more unexpected discoveries from the Messenger mission were the elemental chemistry instruments discovered a lot of sulfur, more sulfur than what we expected, a lot less iron than what we expected. And sulfur is one of these volatiles. Now, when you think of volatiles, think of something that transitions easily from a solid to a liquid to a gas, or goes straight from solid to gas under a short temperature range. Doesn't take as much change in temperature for them to go to a gas. So they're much more easily mobile. And water is just one example, but there's a large group of these materials called volatiles, and Jeff can describe them in more detail. But one of the things we found with the Messenger observations is that sulfur was there in plenty. There's been some indication of magnesium sulfates and calcium sulfates present. There are very unique features that were imaged for the first time by Messenger called hollows. And they are considered some of the youngest terrains that indicate some of the more recent potential volatile loss. So it wasn't far reaching to say, hey, there may be volatiles here. The real innovative and groundbreaking work from what Alexis came up with is the crust is rich in them. And then the indicators are there's a subsurface layer full of these volatiles. And the chaotic terrain that we were looking at is an area where a huge volume of these materials due to the environment. And by mapping the morphology of the region, he could show that, yes, this matches with what we would expect if you had material from underneath removed, large volumes of material removed.
And the fact that we're finding such massive features even today on Mercury isn't as surprising as folks might think, because while we took our first spacecraft images of Mercury before I was born, those images only caught a crescent of Mercury, not the entire world, and they weren't particularly high resolution. It wasn't until Mercury, only about 10 years ago, was visited by the Messenger spacecraft, that we finally had full world maps in any amount of scientifically useful detail for this kind of what is this particular feature as compared to that particular feature mapping ability. Now, prior to Messenger getting to Mercury, what was the story that we had? Jeff, I'm going to go to you.
Okay, so so one of the first really important geologic features that the Mariner 10 spacecraft discovered in the early in the 1970s, I think about 1974, when it flew past Mercury 3 times, was this gigantic impact basin, Caloris. I forget how big it is. It's on the order of 800 or 1,000 kilometers across. So we're not talking about a small impact. It was a huge impact. And of course, an impact like that would generate enormous seismic waves. And the way these would travel from an impact source is they would travel radially away. And since Mercury is a sphere, roughly, they would converge on the other side. And the hypothesis then was that these seismic waves had the capacity to jumble up the terrain, cause landslides and faulting, and just really raise havoc with the landscape, cause craters to fall apart and that sort of thing. And this was the interpretation of the chaotic terrain, which was another major feature discovered by the Mariner 10 spacecraft. And so that idea held sway until Alexis dared to challenge it. And I think he methodically, he and other colleagues besides myself collected the data necessary to show that the chaotic terrain was much younger than the impact, and that threw the seismic model out the window. And I mean, we'll see what that group has to say about it. You know, there's always another side to it, but I think that Alexis has put together a very compelling story, and Deborah and I can speak for myself at least, you know, are very proud to have been a part of this story. And you know, my role has been in dreaming up possibilities that of what comprises the material. And Alexis was first excited about the idea that it could be really very much like Martian chaotic terrain without the floods, but with direct sublimation of buried ice. And I was not so compelled by that explanation because, you know, this is Mercury, you know, 16 times solar radiation, or maybe 15 times the solar radiation absorption that you know, compared to Mars. And so, you know, ice just doesn't seem very plausible, but it's not completely out of the question, because there could have been an impact of a giant ice-rich body from the main asteroid belt or maybe farther out, that if it hit at a glancing blow, it could have put a big layer of ice-rich material on Mercury, and then that would take thousands and thousands of years to break up. And but it still does not. It seems like it raises more unsettling questions and maybe even unsolvable questions than if it was some other volatile or water in a different form other than ice.
So let's work on just pausing for a moment and trying to unpack this, because this is a whole lot of information. So first of all, this is one of those classic cases of correlation is not causation. We saw this correlation between the position of Caloris Basin and the chaotic terrain on the antipode, the opposite side, the if you drilled straight through the world, this is where you would end up. And just like here on Earth, people have seen, well, we have periods of vast volcanism. And before we got precise dates, it was assumed, well, maybe the volcanoes killed the dinosaurs. Well, in this case, without precise dates, it was assumed that this impact basin created the chaotic terrain. Now, a whole lot of energy still ended up in that landscape. But here's where, if I understand, things get trickstery. The way we understand how old this chunk of a planet's surface is compared to this chunk of a planet's surface is by looking at the number of craters. And this is something that a lot of folks out in our audience have helped us figure out with Moon, Mars, Mercury, where we've had a lot of projects to count craters. And what they're doing is, in areas where you see a whole lot of craters, that means that landscape has been open to be impacted by rocks falling from the solar system for a lot longer than that area where you don't see a lot of impacts. There's essentially a evolving but kind of well understood rate at which objects of different sizes hit planets, asteroids, large worlds. And since there's this study rate of things that are falling. No craters means new. Lots of craters, especially lots of huge craters, means old. Am I so far summarizing all of that correctly?
Pretty much.
Yes.
Okay.
That's very good.
That's a good back of the envelope way to describe it.
Okay, so
Craters.
what craters. So along comes Alexis, and he notices in the messenger data that the chaotic terrain there looked like these similar named landscapes on Mars. And he decided to see, okay, how old are these different terrains? And he did what any good surface scientist would do, and he counted craters. This is a long and tedious process, and I hope you guys helped him count craters. Did you help him count craters?
No, Dan Berman did that. No. Yeah, Dan Berman, also another PSI colleague, did the crater counting with Alexis. Yeah.
One of the interesting stories that Alexis told me in discussing his ideas and his papers, back in the 70s, there was a series of spacecraft called Mariner.
Mm-hmm.
As Jeff has mentioned, they visited Mercury. They also visited Mars.
Yes.
And these spacecraft took images of their planets. And the Mariner, I believe it was Mariner 9, I could be wrong, that visited Mars. And it took images and it saw the chaotic terrain on Mars. And these chaotic terrain were the needed evidence to start thinking about hydrology on Mars and the hydrological cycle on Mars. That's what kicked off. It was those sets of observations that kicked off. There's water on Mars. Where is it? When was it fluid on the surface? Where has it gone? So Mars hydrology became a study kicked off by these images.
Does Earth have this kind of terrain that allowed us to recognize it on Mars?
You want to take that, Jeff? I could give a fluffy answer.
Yes and no. Definitely not in terms of the sheer scale of it. But there are terrains on Earth, on glaciers, that undergo meltings. You know, sometimes they're covered in rocky debris, and they undergo melting, and the ice structure develops a Swiss cheese type internal structure that's just filled with water. And the surface of the glacier becomes pitted and jumbled, collapsed. And so that would be maybe the best analog, which is not a very good analog in terms of scale. But it's a similar thing. And there are outburst floods similar to some of the chaotic terrain on Mars. And there are some other geological terrains that don't involve water, that involve movement of the lower crust that causes the upper crust to come apart. There are other terrains involving salt domes that then undergo dissolution in the interior, and they collapse and form jumbled up terrains. And the salt domes don't look a lot like the chaotic terrain on Mercury. And certainly not on Mars, but ironically, there may be more than just a thin thread of analogy to Mercury, in that sodium chloride, is one of the materials that are thought to exist on Mercury. And we think of sodium chloride, ordinary table salt, as not volatile. I mean, you spill some on your countertop, and if you're really a messy homemaker, housekeeper like me, it might still be there days later. And if you happen to leave it for decades, which I don't do, it'll still be sitting there. It's not volatile at Earth surface temperatures, but at Mercury surface temperatures during the daytime, sodium chloride is slightly volatile, enough that over hundreds of millions of years, it would sublimate. And then it goes somewhere.
And
that can be into outer.
This gets at the core definition of what a volatile is. A volatile is any molecule or collection of the same atom. So you can have either a single thing like oxygen, or you can have a compound like carbon monoxide, carbon dioxide, that at the particular pressure temperature combination of a given world, it's going to switch between phases as the temperature on that world changes. So on Mars, we see water go from ice to gas. We see carbon dioxide.
Oh, yeah. Yeah, good. Sorry.
And then on Mercury, we actually have this ion tail stretching behind it made up of salt, which is one of the most confusing and awesome things that you can see in images where Mercury suddenly looks like a comet.
So Mercury is a very complex system. You have this tail that you refer to is actually, it has what's called an exosphere. So that means think of an atom per cubic centimeter. Yes. I mean, this is very, very tenuous, but it has a huge exosphere made of sodium. It also has a magnetic field. And so the sodium can get ionized and travel along the magnetic field, which causes that tail that you're talking about. So where does that sodium come from, and why does that exosphere still exist? Because it can be easily blown away by the solar wind. So it needs to be replenished. That's being replenished from the surface of Mercury itself. So how come we haven't run out of it? Where is it coming from? All right. And so these aren't questions we have answers to yet. But what Alexis has found is a piece of that puzzle.
So okay. What did he find?
He found that Mercury, even though it's so close to the sun, has a reservoir of, or potential reservoir of volatiles beneath the crust. And that in certain places, when it gets exposed to the environment, it sublimates, it goes away.
So this is a situation where you have embedded within the soil, and I know using the word soil is controversial, especially you out there in the Twitch chat who are going to tell me soil comes from earthworms. Within the stuff that Mercury is made of, you have a volatile-free crust in most places, and beneath this is trapped stuff that, if exposed, is going to happily, escape out of that mineralogy, that soil, and go away. Is that a good way of summing that up?
It's going to move. I don't know if it'll go away, but it'll move.
It'll come out of the soil.
Yes, it'll come out of the soil if it has a mechanism like crack, a fissure, an impact that exposes layers beneath. It will move. It will sublimate and it'll move. It's going to find a stable place, a permanently shadowed area. That's why we think we see ice at the poles, just like we think we see ice at the poles of the moon. It will get swept up into the exosphere. So it has places to go, but it's not gone yet, so to speak. It's still within the system.
And as far as the volatiles go, we do see a polar cap of sorts. It's not like the Earth's or Martian polar caps. It's a cryptic, a chemical polar cap, in that the high latitudes are enriched in volatiles. Deborah mentioned the ice that's in the permanently shadowed polar craters of Mercury. But we also see concentrations of sodium, which has been mentioned. Also chlorine, the other component of table salt, and sulfur, which Deborah mentioned. Let me see, and potassium.
And these chemicals are all just the regular everyday mixture of items that were there when Mercury formed. Or did they have to get brought back to Mercury later after its formation?
You're asking a good question. And that's a really, really good question for a future mission, among others. That's my way of saying we don't really know.
Okay.
I guess, I see it both ways, equally, that they may have been volatiles that were Mercury was born with, that accumulated into Mercury when Mercury formed, and then they were expelled. Maybe, think about fumaroles associated with volcanism and other processes.
I don't know what fumaroles are, so sorry.
Okay, so some people who have been to Yellowstone National Park will have seen these, just the hissing, spitting gases shooting out, without involvement of a lot of liquid water.
So these are basically places where a crack in the soil is spitting without a full-fledged volcano being necessary.
Yeah, there may be magma, liquid rock at depth helping to drive this out, or some kind of geothermal heat. And we know that Mercury has a metallic core, which means that metal melted in Mercury. That certainly is hot enough to drive out a lot of volatiles to the surface. And so the other possibility is that it was a late veneer of cometary material or some kind of water-rich and other volatile-rich material. And one thing that I'd like to mention, you mentioned earthworms and soil, kind of in well, not kind of, definitely joking, but you opened up this program talking about life, and I said, well, I'm kind of skeptical of that, but I'm also intrigued by that idea. And there is one slender thread of evidence interpreted just the right way, wearing your life-colored goggles. And that is, Mercury is a gray planet. We talk about Mars being the red planet, and it's red because of iron oxides, and that's probably because of the role of water in the past. Well, Mercury is gray. It's gray, 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 and it's dark gray. And that's something that Deborah has looked at, the colors of Mercury. There's scant little color. There's this nondescript substance. Do you want to say something about that, Deborah?
So one of the things that the elemental chemistry found was carbon. I think that's the magic element that people are hinting at here. And the formation theories for the crust and what the crust is like. One of the ideas out there is that there was a carbon flotation crust when when Mercury was forming, when the crust was cooling off to become solid, that the carbon came out of the magma and it floated to the top. And so we have a layer of carbon on the top. So, Graphite.
That's the interpretation.
That's the structure of the carbon. Graphite is a structure of carbon.
Yeah.
Correct.
Pencil lead.
But
okay, lots
that
of
carbon could also have integrated into the mineralogy of the upper crust. So you have that element there. The carbon is there in the crust. And so now you're out of my level of expertise here.
Okay.
In terms of the chemistry that can invoke.
Okay. I would like to throw out a different interpretation of that carbon. I'll say, yeah, okay, I like the idea that it's graphitic, like maybe not exactly graphite. Some of it could be graphite, just elemental carbon in polymeric chains, the stuff that forms pencil lead. But also could be, highly disordered carbon-rich material. It could potentially even include a component of what geochemists call kerogens.
Okay, so what are
Dark,
kerogens? It's
they're carbon-rich remnants. If you take earthworms and leaves and living things, and actually it can be carbon in just about any form, and you heat it and cook it and cook it and cook it. We know about the formation of petroleum. We know about on Earth. We know about the formation of coal. If you take that coal and heat that and cook it more and cook it more, you drive off the hydrogen, you transform that organic material in the extreme, it forms graphite. Okay, and there's a host of other graphite-like substances that are still organic. They still contain some hydrogen, but not very much. And it doesn't mean that I like the idea of the graphite flotation crust, but I also like the idea of earthworms and leaves. I mean, not literally, but living things, possibly a biosphere that was completely killed and then completely metamorphosed to something that we call kerogens, which exist in high grade, highly heated metamorphic rocks on Earth. In fact, the oldest evidence of life on Earth isn't fossils. It's not the fossil stromatolites, the algae fossils that you hear about. Older than that are kerogens in metamorphic rocks, and through various geochemical and isotopic means, it has been linked to living stuff. Now, if Mercury had a really vibrant ecosystem, I already said that I'm skeptical of this whole idea, and I am, but at the same time, it's an intriguing thought, and I can't dismiss it, that there may have been, maybe a very transient ecosystem,
and
maybe lasting a very brief time. Go ahead.
And one of the things that makes this kind of a seemingly insane idea conceivable is worlds in our solar system have moved around. Mercury didn't need to start where it is today. And it also takes time for, the sun to have a chance to completely bake something dry. So we could have started out with a much more chemically nuanced world with a lot more volatiles, a lot more water. We could have started with Mercury potentially in a different place where it wasn't getting blasted so hard. We can tell from the cracked structures that somewhat define Mercury and from its overly large core that this is a world that used to be very different from what we see now. And all of these things make the impossible seeming actually quite possible potentially, which isn't the same thing as it was. It's to say we need to send robots and look.
And the sun, it was the same sun, but it was a cooler star. Not a lot cooler, but everything. The sun is a main sequence star. It's kind of an ordinary kind of star, and we know how stars evolve as they burn up their hydrogen fuel for reasons that I won't go into. The sun, like other main sequence stars, is brightening. It's becoming a hotter sun, and the sun when Mercury and the other planets were young planets was about 70% as radiant as it is now, which still it would be a pretty hot planet even if Mercury was a little bit farther out in the solar system, a little bit more towards where Venus is today. But you start taking these individual pieces and put them together. Mercury maybe having been a little bit farther out in its orbit, the sun having been a cooler star, and weird things happening in the solar system, and you could have had a very different Mercury.
Now
We're not.
let's try
Go
and
ahead.
circle all of this back to where we started, which was this article in Nature looking at the chaotic terrain. So, roughly when did the Caloris impact basin get formed by whatever huge monstrosity knocked the bejesus out of Mercury?
3.8 billion years ago would be sort of the canonical idea, that about the same age as the giant impact basins on the moon, which have been directly dated from the Apollo and Luna missions. You can play around with different models and come up with different ages, probably by just a little bit different, that, to planetary scientists, that is really important. But roughly 3.8 billion years ago would be probably when Caloris formed.
So this was the age of the great heavy bombardment when bad things were happening everywhere.
Yeah, on Earth too.
Yeah, we're part of everywhere usually. Now, with your crater counting, what age did you come up with for the chaotic terrain, or did Alexis and Dan Bierman come up with?
1.8 billion years. Again, with uncertainties about
Yes.
the impact cratering history, the rate of impacts. Some people would live and die on their crater count chronologies. I'm not one of those people, but it was much, much later than Caloris.
So crater counts with certainty. We can say this is older, this is younger. With the moon, we can, with much greater surety, say if you have this density of craters, it is this age. If you have this density of craters, it is this age, because we have sent humans and robots to collect rocks and bring them back, and we've used various methods of age dating to figure out the ages of those rocks. We have an episode of Astronomy Cast. Go watch it. Now, with other worlds, however, because we haven't yet collected rocks, we have to hang things off of we know what that means on the moon. We make these assumptions about how much more common or less common impacts are on these worlds with different gravitational wells that are different distances from the sun. And so we can say with certainty older or younger, but 1.8 is a convolution of, yes, it's younger, and our models tell us probably 1.8 billion years.
Yes, you've got it.
So as you look at this, what on Mercury might have triggered this spontaneous, this region and this region alone shall give up its volatiles and do bad things to the landscape?
Okay, I want to make one correction there.
Okay, please.
The paper focused on what we call the antipodal, that is the Caloris antipode chaotic terrain. But one of the other things that Alexis and also Greg Leonard, one of our colleagues, he's an astronomer who works at the Catalina Sky Observatory. Normally he's hunting for near-Earth asteroids. But he did most of the geologic mapping with Alexis's guidance. And they found that there are chaotic terrains scattered over much of Mercury's surface.
Oh, good Lord.
Yeah, they go even to high latitudes. So, but to get to your question, there are kind of two different ideas that our team is working with. One, which I think Alexis mostly favors and which fits in fairly well with some of the other Mercury scientists who are not on our team, is that there was a period of volcanism. And in the chaotic terrain, it wouldn't be lava pouring out onto the surface, but it would be magmatic underplating, that the magma, the liquid rock, found a place where it could flow out underneath this volatile rich layer, because it would presumably have been denser than the volatile rich layer. And then the heat cooked out the volatiles even more.
So this is very, very loosely, this is a somewhat criminal analogy I'm about to use, but this is very loosely like when we know that there's volcanic activity on Iceland because we see a sudden flood from a glacier.
Yeah. That would be a really good, very, very good analogy, not too criminal at all.
Okay.
Now, there is another possibility, but again, this is totally, both of these ideas need another space mission. But there's another possibility that instead of bottom-up heating, it was top-down heating. We've talked about that already, the sun,
Yes.
that solar heating drove this off. If this is the case, then it would mean that, since these chaotic terrains are found at different latitudes, which presumably, have different temperatures, then there would be different timings of the release of the volatiles. And this is something that with better data, and actually even just a more careful look at the messenger data, we might be able to pick up if there are different crater count based ages. I would predict the higher latitude ones would be younger because the sun is brightening. We mentioned that Mercury could be migrating inward a little bit in its orbit, so getting closer to the sun. So Mercury would be heating up, and the higher latitudes would basically take longer to heat up to the magic point where the volatile sublimate. But there's a further complication. We've talked about mainly about ice and sodium chloride, but there's a host of other volatile materials that are possible. I mentioned earlier organic materials. They're volatile.
Oh yeah.
There are various sulfides that Deborah mentioned. Sodium sulfide would be a prime candidate. Calcium sulfide and magnesium sulfide are believed to occur in the hollows regions, but those are actually refractory. They're not even volatile, but they could be the sulfide stuff that's left as a remnant after the volatile sodium sulfide and some other sulfides like potassium sulfide sublimated away and either went into space, into the exosphere that Deborah mentioned, or migrated towards the poles.
So this is very much a confusing story of which chemistry did it, where there are a whole host of different molecules that, depending on what the temperature was at any given point in time, what the materials either brought to Mercury through impacts or left in Mercury from its formations were there. Depending on this combination of composition and external temperature, different things could be to blame for what we're currently seeing. Now, Deborah, you were one of the chemists on the project while other folks were going down more of an astrobiology bent. What was it like to be part of this team while folks are trying to do the straight and narrow, count the craters, figure out the cause, with this life always in the background of the discussion? What was that like?
So for me, I don't think you're going to find life on Mercury, in all honesty.
And that's okay. This is why I'm asking you the question.
But it's about the implications.
Yeah.
If you can have volatiles retained on this object so close to its primary, to its star, what about all those exoplanets out there? That opens the door for volatiles being a component to planets close to their star, close to their sun. And if you can have volatiles, carbon, water, etc., retained on objects close to their star, then you have the ingredients for life. And then the question becomes, all right, what are the environments that would say, okay, I can kickstart life here, but I can't over there? And we don't know the answer to that question. And by looking at Mercury, we can get a better constraint on what are the conditions for life to get kickstarted and go. And so that to me is the intriguing part. Not that we're going to find prebiotic material on Mercury. I have my doubts. But what we can understand from looking at Mercury are what are the mechanisms for retaining volatiles? What are the mechanisms for volatile loss? And how long can these volatiles be a vibrant component of the crust?
And so let's unpack this a little bit. We're in this weird moment where, if folks can remember the Drake equation, there's a lot of different things in it that you have to take into consideration. How frequently are stars born? How long do they live? What fraction of stars have planets? We didn't know that until recently, and now it kind of looks like most of them that have the right chemistry. Then once you start to have planets, we start to get to, this wasn't as formalized by Drake, but now we're realizing this is an issue. How often is the chemistry necessary for life present? This used to get taken care of how many of these planets are within that Goldilocks zone in distance from the sun, where you're capable of having water at its triple point at the surface of the world, so you can have water in a liquid form, potentially an ice, potentially a gas, allowing rain and ecosystem. But now we're realizing, because geology likes to confuse us, that, oh wait, you can have liquid water due to tectonics, due to volcanism, we still haven't figured it out, at moons and asteroids all throughout our solar system. So as we start to consider the Drake equation, we're getting to the point of, now we have to do how often does the chemistry support life? And then we have to look at how easy or hard is it to form life? And we're at the stage where we just need more robots, because there are folks like you, Jeff, who are like, life must be easy to form. And if it's easy to form, even Mercury might have been coated in a sludge of amoebas that then, well, even life can be sublimated
and
if
you do bad things. And earthworms.
Pamela, I would agree with Deborah in that I really am skeptical of the idea that there's life there. But, 20 to 1, no life, no prebiotic, no postbiotic, but maybe there was. But I also want to, I personally would rephrase one thing you said. You said,
Please.
It's sort of a confusing story. Just because we don't have the ability to answer your questions, it's confusing. No, it is an exciting mystery story.
That's true.
Well, what's really nice about these what if scenarios is they make us think outside of the box. Okay. And this discovery of this volatiles on Mercury is because Alexis has a talent for thinking outside of the box.
Yes.
Right.
Yes.
And so even when somebody states an idea that you could say, oh my God, that's crazy. Listen to it.
Yeah.
Because if the evidence is there, then you have to find evidence to disprove or substantiate. Okay. What evidence do we have? And that's what we're looking at. And by looking at what we have, we now know what other questions to ask. And by knowing a new set of questions to ask, we know what to look for.
If you could design any spacecraft, Deborah, what questions would you design that spacecraft to answer?
Composition.
Composition.
Big thing. Composition.
So is this a mass spec and a core driller? What composition do you want to get at?
Well, so it's not just what's on top.
Yes.
But it's composition of what's underneath. And it's not just composition of what's in one place, but what's in multiple places.
Yeah.
And how is that composition altered by the space environment so that when I can't get down on the ground and measure things, if I measure things remotely, I have a way of interpreting that. I know how the environment alters my chemistry. I want to understand that. I really do. So a lander would be great, and a lander that can hop around, or multiple landers. You know, if you, somebody said, if I give you a blank check,
Yes.
you know, so that's the big thing that I want to get at is what is it made of, not just on the surface, but as you go with depth globally.
And I definitely echo that. I definitely do. There are two kinds of chemistry experiments, broadly speaking. One is what's the stuff that's sitting there and has been sitting there and has moved around, and what currently is moving around. Because we see
and
the exosphere.
Here you're talking about through chemistry and gravity, not because it has feet.
Correct.
Yeah. So I think chemistry, and both inorganic, like sodium and chlorine, for example.
Yes.
And I would go for organic chemistry, because certainly organic material is present on Mercury, at least co-deposited with the ice in the permanently shadowed impact craters. It might not be very much. It might not be very interesting from a life perspective, but we just might be surprised and discover that there are highly metamorphosed remains of organic materials, whether due to life or just due to carbonaceous asteroid material, not related to life, sprinkled throughout the Mercury surface materials and upper crust.
I watched a truly terrible dystopian fiction movie on an airplane not too long ago, but before the current plague. And it was British. And it included these massive cities on tank treads that ground across the surface of the planet. And they had full capabilities of stopping and doing oil wells where they went. And while I'd like to escape the dystopian future that some days we seem to be headed towards, I would like to have these massive cities on tank treads to put on worlds like Mercury, where if you can just stay at the right place at the terminator, you won't overheat. And imagine with its super slow rotation, if you could build, well, essentially those oil drilling platforms, except all you're after is a core sample that you're going to process as you pull it up. That is my fantasy. Escape the dystopian future and put the giant robot cities on other worlds.
Good idea. Blank check you mentioned, right?
Yeah,
I think Deborah mentioned. Yeah.
So I have kept you for an hour, and this has been an amazing frolic through the science of Mercury. And I'm so glad that both of you were able to join me today. If folks want to keep up with your ongoing research, where should they go to see everything the two of you are up to? Deborah, I'm going to start with you.
Well, usually the interesting stuff gets posted on the PSI front page.
And we will bring it to you folks right here on CosmoQuest. Go ahead. What else?
That's where, we advertise, look in the journals, Science, Nature, Icarus.
and there was a New York Times article that the headline caught an offhand comment I made. The headline of the article was something like, life on Mercury, it's nuts, but not completely nuts. I think that's about where I am. But the volatiles are more secure. We just don't know what they are.
Yeah. I appreciate that concept. And I would like to send a shout out to State Space Signal, Evil Hippie, John Peake, all for following us during this interview right here live on CosmoQuest X on twitch.tv. Now, I've asked my questions. Is there anything I didn't ask that you'd like to make sure that everyone knows about this research before I let you go?
Yeah, I have one question. Would you please write the next paper and we can edit it? Uh, you, you've done a really darn good job. Really, you're right up on the issues.
Thank you so much. I'm always happy to collaborate, and I'm not gonna lie, I would absolutely love to work with you guys on a crater counting project where we can work together to well, let's see.
Let's talk to Alexis and Dan Berman and let's make it happen.
Yeah, and for all of you out there watching, we have a test edition of our newest citizen science software available on sandbox.cosmoquest.org. The data isn't getting saved to do science, it's getting looked at to figure out what we broke. But if you'd like to get engaged in helping us, well, help scientists like this, join us over on our Discord. Links to everything are on cosmoquest.org. It has been great having the two of you here, and I'm gonna go ahead and release you to keep doing that science and switch over to ending out this episode. So thank you so much, Jeff, Deborah. It's been great having you on today.
Yeah,
Thank
thank you.
Bye-bye.
Yeah, bye-bye.